on density and related notions in anti-topological spaces. Anti-topological spaces have been introduced by Sahin, Kargin, and Utel in 2021, and they are among the newest inventions in the huge world of generalized and modified topologies. And in some sense, they are connected, or they may be considered together with so-called neutral topological spaces introduced by the same authors. And these neutral topological spaces have certain relationship with Smarondach's neutrosophic sets. Um, we've already presented some basic results on anti-topological spaces in our previous video. And now we would like to discuss, as you can see here, the notions of density, knower density, and rarity in the anti-topological context. And as for the further studies on this topic, we have analyzed anti-topological spaces in two papers. Look at the bibliography, they are here. One of them is available on Archive.org as a preprint, and another one, well, to appear, as you can read, you may contact with me if you are interested. Um, well, assume that x tau xt is an anti-topological space and there is some set A contained in X in our universe. And then we say that A is anti-dense if anti-closure of A is just X. Anti-knower dense if anti-interior of anti-closure of A is empty. Strongly anti-knower dense if it has empty intersection with any anti-open set. This definition here is in some sense more strict than in case of, let's say, topological spaces. You may check in our paper why is that so. And it's anti-rare if anti-interior of A is empty. As for the notion of anti-interior and anti-closure, they are just like the notion of interior or closure in, let's say, Avila's and Molina's generalized weak structures. I mean, interior is just a union of all, in our case, anti-open sets. So interior of A is just a union of all anti-open sets contained in A. Yes. Now we encourage you to analyze these examples, like this one. For example, we have this universe, 1, 2, 3, 4, 4 elements. This anti-topology, 1, 2, 2, 3, 3, 4. And one can check that, for example, these two sets, 1, 2, 3 and 2, 3, 4, are anti-dense, according to the definition from the previous page. As for this set, 1, 4, it is anti-knower dense. However, it's not strongly anti-knower dense. So it means that strongly anti-knower dense, as we could see, it means that it has empty intersection with any anti-open set. But in this case, it's not true. Yes, A and let's say 1, 2. A, in our case, A is this one, yes, 1, 4. Its intersection with 1, 2 gives us singleton of 1, which is not empty. In this case, we have 6 elements, A, B, C, D, E, F. This is our anti-topology, A, B, C, D, and singleton of E. And for example, F is strongly anti-knower dense. Clearly, it has empty intersection with any anti-open set from this collection. Again, the same anti-topology as earlier, but now you can consider these sets 1, 3, 1, 4, and 2, 4, and they are anti-rare. And well, these examples are rather simple, yes? You could say that these are just several finite spaces, finite universes, but you may find other examples, sometimes less trivial, more sophisticated, in our papers from the bibliography. One can prove some lemmas and theorems concerning, referring to the these notions introduced earlier. In general, we'll skip the proofs, so these are just theses. For example, one can prove that every strongly anti-knower dense set is anti-nowhere dense too, but the converse need not to be true. We already know that the converse may not be true, uh, clearly from this fragment, which is here. Um, then, if A is anti-rare, then for any anti-open B, B is not contained in A. Any non-empty and proper subset of anti-open set is anti-rare. Yes. Every anti-nowhere dense set is anti-rare. Moreover, if we have anti-topological space and A is contained in X, then A is anti-rare if and only if its complement is anti-dense. An intersection of anti-rare sets is anti-rare too. And on the other hand, any union of anti-dense sets is anti-dense too. Finally, A is anti-dense if and only if it has non-empty intersection with each anti-open set from T. This is very typical, yes? In general, some of these results are typical for topological spaces too, or even for generalized weak structures, yes? So I couldn't say that each of them is specific, is characteristic just for anti-topological spaces. This wouldn't be true. You might find other lemmas and proofs and properties and examples in our papers. And in general, we would like to investigate other topological notions, like connectedness, convexity, compactness, separation actions, continuity, weakly open sets in the anti-topological framework. So this is our bibliography. If you are interested, please comment, please contact with me. Thank you very much for your attention.